Okay, we are going to start this 5-step problem solving for the pH of a weak acid, strong base titration. So this is part 1 of 5 parts. So in the previous video, I explained what titrations and titration curves were, and I laid out this problem where we are going to solve for the pH at each of these 5 points, and then we're going to make a titration curve by plotting these 5 points on a graph. So here's the problem that we'll be referring to in each of these 5 examples. Find the pH at each of the following points in the titration of 25 milliliters of a 0.30 molar hydrofluoric acid, that's what would be in the flask, with 0.30 molar sodium hydroxide. And then also given is the Ka of hydrofluoric acid, 6.6 times 10 to the negative 4th. What we're doing in this first problem is part 1, the initial pH. So what that means is we have our burette that has our sodium hydroxide in it, and we have our flask. Inside our flask is the hydrofluoric acid, and we have in here 25 milliliters of a 0.30 molar hydrofluoric acid solution. In the, make sure I wrote that down right. In the burette, we have 0.30 molar sodium hydroxide. So part 1 of this 5-step titration is the initial pH. So this means, what is the pH in the flask before any sodium hydroxide is added? So this is the initial concentration. We've not added any sodium hydroxide yet, so this is just kind of our starting point. What is the initial pH? So to solve for the initial pH, we just want to know what is the pH inside this flask, and we have the initial concentration of hydrofluoric acid. We don't need to do anything with the volume because we have the concentration, and we are not changing the volume. When we start changing the volume, then we will need to change things. Okay, so let's just write our equilibrium table, because this is, all we are doing here is a weak acid ionization. That's the only chemistry happening here. What we're going to need to do is address what chemistry is happening at each of the 5 steps, because it's going to change, and we need to know what calculations we do depending on what kind of chemistry is happening. So the chemistry that's happening initially is just a weak acid ionization in this flask. So the reaction, I'm just going to write the generic equation. The initial concentration is 0.30. Water is not included. I don't have any hydronium or any conjugate base. Minus x, 0.30 minus x, plus x, x, plus x, x. So now I'm going to solve for the pH by solving for the concentration of hydronium at equilibrium. And I am going to assume x is negligible for all of these problems. You'll see that if you do the calculation, 0.30 divided by 6.6 times 10 to the negative 4th, which is the Ka of hydrofluoric acid that was given previously, it's not quite 500. So let's just assume x is negligible and then see if it makes a difference. If it does, we can always go back and do the quadratic formula, but let's just assume x is negligible for now. Okay, so also remember the Ka of hydrofluoric acid was given on the previous lecture, 6.6 times 10 to the negative fourth. Okay, so let's solve. So I'm going to say Ka 6.6 times 10 to the negative fourth equals x times x squared, over 0.30 minus x. I'm going to assume this x is negligible, 0.30. Multiply both sides by 0.30. Take the square root. X equals, so let's say 6.6 times 10 to the negative fourth times 0.30 square root 0.014 or 1.4 times 10 to the negative 2. So that is my X, that's my hydronium ion concentration. Let's just double check that this doesn't change the concentration here. 0.30 minus 0.014 with two significant figures is 0.29 instead of 0.30. It's close. I would allow you guys to assume that X is negligible for a problem like this. It's close enough. Okay, so here is my X. This is the hydronium ion concentration at equilibrium. To solve for the pH, we're going to say pH equals the negative log of the hydronium ion concentration, 1.4 times 10 to the negative 2. Negative log of 1.4 times 10 to the negative 2 is 1.853. I'm going to say pH equals 1.85. Depending on what numbers you left in your calculator and how you did this, your answer might be off a little bit. Anything close to this would be fine as long as it matched up with your work and you had the correct number of significant figures. Two significant figures in the concentration. That means 2 decimal places in the pH because of the log rule. So that's my pH initially. So that is part 1. Part 1 asked, what is the pH in this flask before any sodium hydroxide is added? So if we were going to draw a titration curve where this is the pH and this is the volume of sodium hydroxide added, the most we're going to add, we'll say this is 30, 15. So we have added 0, let's say pH, let's say this is 14, 7, okay, so here's my graph. This is the pH. This is the volume of sodium hydroxide added. When we have added 0 milliliters of sodium hydroxide, the pH is 1.86. So I'm going to put it right here. So part 1, 0 milliliters sodium hydroxide. pH equals 1.86. Sorry, 85. That's what we decided. So there's part 1. No sodium hydroxide added. The initial concentration in the flask, the pH is 1.85. So that's the first point on our titration curve.